Here's something that should make every mechanical engineer stop and think. A conventional gas turbine plant takes perfectly good fuel, burns it, generates electricity, and then throws away more than half the energy as 600-degree exhaust gas straight into the atmosphere. Combined cycle plants don't do that. They capture that wasted heat and turn it into another third of the plant's total electricity without burning any extra fuel. That single engineering decision is one of the most elegant efficiency improvements in the entire history of power generation. Combined cycle gas turbine plants, CCGT, currently produce roughly 20 to 22% of global electricity and serve as the backbone of flexible generation in many countries. A simple open-cycle gas turbine converts about 38 to 42% of the fuel's energy into electricity. A modern combined cycle plant using the same fuel reaches 62 to 65% efficiency. That 23 percentage point jump doesn't come from better combustion. It comes from not wasting the enormous amount of heat that the first turbine already created. Let's break down exactly how this works. The first half is a conventional gas turbine running the Brayton cycle. Air is compressed to about 22 bar, heated in the combustor to roughly 1,500 to 1,600 degrees Celsius, expands through the turbine, and exits at 580 to 620 degrees Celsius. That exhaust is still extremely hot. In a simple cycle plant, this is where the story ends. In a combined cycle plant, that hot exhaust goes into a heat recovery steam generator, or HRSG. This is essentially a giant, sophisticated heat exchanger. The exhaust gas transfers its heat to water, generating steam that drives a second turbine. The same Rankine cycle we covered in the previous video. Modern HRSGs use 3 pressure levels, high, intermediate, and low, to extract as much energy as possible across the entire temperature range of the cooling exhaust gas. The exhaust enters at approximately 600 degrees Celsius and leaves the stack at only 85 to 100 degrees Celsius. Almost all usable heat is captured. The steam turbine in a typical combined cycle plant produces about 30 to 35% of the total electrical output, essentially free power from heat that would otherwise be lost. The most common setup is called 1 + 1 + 1. 1 gas turbine, 1 HRSG, 1 steam turbine. Larger plants often use 2 + 2 + 1, 2 gas turbines feeding 1 larger steam turbine. This reduces the cost per megawatt. A modern 2 + 2 + 1 block with H-class turbines can produce 850 to 900 megawatts from a relatively compact site. The biggest challenge for CCGT plants in 2026 is not efficiency, it's daily cycling. As solar and wind penetration grows, these plants are forced to start and stop much more often than they were originally designed for. The component that suffers most is the HRSG, specifically the tube-to-header welds. Thermal fatigue cracking has become the leading cause of forced outages in cycling plants. However, the best operators are solving this with real-time stress monitoring and smarter startup procedures. What used to be a serious weakness is rapidly becoming a manageable engineering problem. 3 major developments are happening right now. First, H-class turbines continue pushing efficiency. Modern machines regularly exceed 64% in combined cycle, with some plants reaching 65.4%. Second, hydrogen readiness. Major manufacturers are certifying H-class turbines for increasing hydrogen blends with a clear roadmap to 100% hydrogen by 2030. The plant stays the same, the fuel changes. Third, digital life management. Real-time fatigue monitoring systems now track the actual remaining life of critical components, allowing operators to run plants more aggressively while staying safe. 3 things to remember. 1. The combined cycle architecture is one of the most thermodynamically elegant solutions in power engineering, capturing waste heat to generate a third of the output at almost 0 additional fuel cost. 2. In 2026, the main operational challenge is daily cycling. Plants that manage HRSG fatigue intelligently are pulling ahead. 3. Combined cycle plants are not a temporary bridge. With hydrogen co-firing, they are becoming one of the most flexible, dispatchable, and future-proof forms of firm generation available at scale. The previous video on this channel explained why steam turbines still generate more than half of the world's electricity. Today, we saw how they give combined cycle plants their massive efficiency advantage. In the next video, we'll look at one of the most important and elegant devices in all of engineering, how a heat exchanger transfers enormous amounts of energy between two fluids that never mix. If something here was wrong or incomplete, the comments are open. Subscribe if you want the next one. See you there.